Hi class, we are on to the next section and last section of chapter 7. So we're going to be finishing up the Laplace transform. So we're basically going to be talking today about how the Laplace transform applies to systems of linear differential equations. Now, the next chapter is all about systems of differential equations, which is really nice. If you've taken linear algebra already, then the next chapter is going to be a breeze for you. But for us right now, for the Laplace transform, we've done a lot of Laplace stuff, so you should be semi-comfortable with it at this point. The Laplace transform is nice for systems of linear differential equations because what it does is it basically just takes the system of differential equations and it turns them into a system of linear algebraic equations, right? So again, remember the way that Laplace works is it takes it from the world of derivatives and integrals and, well, still integrals, but derivatives and things like that, and turns it into basically just algebra, right? A lot of rational functions, partial fraction decomposition, common denominators, all that stuff that we should all be pretty proficient at this point by, right? So it's nice for systems of DEs because it just turns it into a system of equations, right? So things from like algebra 1, algebra 2 basically. So that's the nice part about this. So again, the Laplace transform takes our system of differential equations and it turns it into a system of linear equations that we can solve algebraically, right? So an example of this is just to throw a wrench in there a little bit, we're going to derive an equation and then solve it with the Laplace transform. Okay, so if you go back to chapter 5, where we talk about higher order differential equations, we had some stuff with spring constants and mass spring systems. And so that's basically what we're going to do. We're going to have a mass spring system. Okay. Normally we started off, I believe, with a single mass spring system. Maybe there was a couple of coupled springs, which is 2 springs and 2 masses, but now we have 3 springs and they're bounded on both ends, right? So we're going to come up with a system of equations to model x1 and x2, obviously, which is our functions, which tells the position of the masses at a certain time t. And we're going to take that system and we're going to solve it with the Laplace transform. Okay, so here we have really, really nice values for my masses and for my spring constants. All of the spring constants are 1 and the mass of all of these blocks are 1. And we have some initial conditions. So again, remember what the Laplace transform does for us for differential equations is we need our initial conditions to be at 0, which is very, very nice because that's pretty much the standard position of a lot of initial conditions, right? So when we do the Laplace transform on our system, we can just plug in basically these values once we start to find those derivatives under the transform, okay? And it's nice that a lot of them are 0 and we have a 1 and a -1. So we got nice values here, okay? So this problem shouldn't be, I'm not going to say it's not too difficult, but it shouldn't be too crazy because we have nicer values going on here. Okay, and as you can see, this picture takes up half of the slide. So as we build this equation, I'll move backwards to reference this. So get ready for a little bit of moving around. Apologies ahead of time. But we'll jump straight into it. Okay, so this is my system of equations. So we're looking at the second derivative of x1, right? So that's going to give us some sort of acceleration of the mass, right? So if you want to go through a full derivation of some of these, again, go back to your chapter 5 materials, but we will talk about these. So we'll talk about the what's happening to x1 first, and we'll build that equation, and then we'll talk about what's happening to x2, and then build that equation. Right? So what we're going to do is we're going to think about what happens when both of my masses are stretched. Okay, so I'm pulling down m1 and I'm pulling down m2 to some point. Okay, so if you think about this, we're looking at just what affects x1, okay? If I'm pulling down m1, my spring k1 wants to restore M1 to its original position. It wants to pull M1 in the negative x1 direction. That's what this first part is here for. Okay, K1 is pulling M1 into the negative direction, which gives me that first term. Right? So that's how we're going to build this piece by piece. So if this is stretched and this is stretched as well, okay. Now the movement of M2 is contributing to the movement of x1, right? This spring is pulling M1 down when M2 is pulled down, right? So when M1 and M2 is pulled down, so first of all, pulling M1, K1 wants to bring it back. If M1 and M2 is pulled, M2's spring is also pulling on M1, but it's pulling it in the positive direction, right? That's the K2 X2, right? Okay, so the X2 movement that I have is making the K2 spring pull, and it's pulling it down a distance. Not only am I pulled down because of the weight, but I'm also being pulled by this as well. So the X2 distance is contributing to the X1 distance, right? This X2 spring wants to contribute to it. Not only that, but the K2 spring also wants to have a restorative force pulling this way. This K2 is pulling this way, and it's pulling this way when you stretch it out. So it has to pull this X1 down, and it's going to be pulling this X2 back up, okay? So this is what we have. So K2 pulls X1 down, and K2 to the negative direction, and it also pulls this one down. We can do the exact same thing for X2. Okay, that K3 spring is pushing. I guess let's go back here. Okay, when these are both stretched out, okay, what's acting on X2 is the restorative force of K3. When you compress a spring, it wants to push it away. So K3 is going to be pushing M2 back towards the negative direction. Okay, so when this is pulled, you also have the spring of K2, which will be pulling this down and also trying to pull X2 back. So you're going to have X1 coming in the positive direction and X2 pulling X2 in the negative direction as well. Okay. Okay. So K2, oops, sorry, let's move to the next one. So K3 pushes against the X2 direction. The K2 is also going to pull it in the next direction, and then the K1 is going to be compressing down due to that spring constant of K2. Okay. So now that we have this equation and we talk quickly, briefly, again, you should just replay this video if you want to go through that again in more detail. In order to add these values, we have all these values are 1, right? So plugging that in, everything is going to go to 1. So I have some negative ones and some positive ones, and it looks like this. So so I have negative 2 x1s and negative 2 x2s, and I can move those around so it's x1 and x2, x1 and x2. Okay. And then if I take the Laplace transform of each of these, it looks just like this, right? So the Laplace only has to go over the function. Those constants, as we know, get to come out, right? It gets to get pulled out. So this is what my Laplace transform will look like. Obviously, I haven't actually transformed anything yet, right? But just taking the Laplace of each term looks like this. So when I do this, the only thing that's going to change a little bit are the derivatives, right? So we have the rule for taking first, second, third, whatever nth derivative inside of a Laplace transform. These are just going to turn into capital x1 of x, capital x2 of x times their respective scalar values, right? So it's going to look like this. So this side looks exactly the same with their scalar multiples. It's just the capital versions of the functions, x1, x2 that I'm looking at. Here, these secondary primes here are going to be expanded in the same way, but with their respective functions. So x of 1s and x of 2s. So remember the large x1 of s's, those are the capital functions in s. These are the actual x functions evaluated at 0, right? So remember again, that's one of the benefits of having initial conditions at 0 when you're taking Laplace transforms of differential equations. So we have values for these. Some of them are 1, some of them are -1, some of them are 0. So we'll just go ahead and clean this up by plugging those values in that I have here, right? So again, 0, 1, this was 0, this was -1, everything else is staying the same, right? So now I would like to clean this up, okay? I have the same thing on both sides. So let's put this into a standard form because this is now an algebraic problem. These are no longer, these are in terms of functions, right? Functions with a variable, input variable of s. I want to solve this algebraically, okay? So what I'm going to do is I'm going to put the x1s and x2s all on one side and put the constant terms on the other side. And it should look like this, right? So when I add this over, I can pull out that constant capital X1 of both sides, and I have s squared plus 2, right? This turns into a -1. This one moves over to be negative. Same thing on the bottom, s squared plus a 2 minus an x1, and this moves over to be positive. So this is my current system that I want to solve. I just need to isolate x1 or x2. It doesn't really matter which one I go for. I just got to go for one. So let's be nice and go in order, okay? So I think I solve for x1 first. So what that means is I'm going to try to eliminate x2. So again, it's a system of equations, two variables. Solve it however you know, right? I'm going to use elimination. If you wanted to, you can isolate x2 here and substitute that into the other equation. If you want, you'll get the exact same thing. So if I want to isolate x2, they already have different signs. So I just have to get the coefficients to match up. So I'm going to multiply this whole thing times s squared plus 2. So I can add them together and get these x2s to cancel. So when I do that, this will be s squared plus 2 squared. This will be minus s squared plus 2. This will be negative s squared plus 2 as well. So when I add those together, this is going to turn into s squared plus 2 squared minus x1. And this is going to be negative s squared plus 2 plus 1. And this is going to go away. Right. Okay. So I have s squared plus 2 squared minus 1. Both of those have x 1, so I can pull that out. And then this is negative s squared plus 2 plus the 1 value here. And so I would like to isolate this s squared of s. And so I can divide that on both sides here. Okay. And I have the following. So what I did here was just distribute this. So you got the negative s squared minus 2 plus 1. So that gives you negative s squared minus 1. So I just pulled that out and then I expanded this, right? So you get s to the 4th plus 4s plus 4 minus the 1 gives you this value on bottom. And here you can see I just keep the -1 on the side. I don't actually know why I did that. It should just be negative s squared plus 1, but whatever. So what I want to do now, however, right, is notice that this is factorable, right? This is 3 and 1. So I have s squared plus 3, s squared plus 1. So that s squared plus 1 cancels with the other s squared plus 1. And that negative is still there. So I have negative 1 over s squared plus 3 for x1 of s. Okay. So now that I have that, I can take that and plug it into one of these equations that I have here for x1 and find x2. So it looks like the easiest one to work with, is probably this first one, because there's only one x2 and it doesn't have a scalar in front of it, and so I can just sort of manipulate it, right? Or I guess I'm looking at this system here. So this is probably the easiest one because all I have to do is move this over and move that over and then plug in for x1 and I have my value, right? So using that first equation, okay, s squared plus 2 x1 of s minus x2 of s equals 1. I'm going to plug in my x1. First, let's move my x2 around, right? So I will add 1 and move this over so that it's positive, right? Or move this over, change signs, whatever you want to do. But you will have 1, because this will now be positive. And then I will have my s squared plus 2 over s squared plus 3, and then that negative sign there, right? So this is what I'm going to have. Make your common denominator and start to add some stuff together, right? And so notice that pretty much everything cancels out, and I'm left with 1 over s squared plus 3. So very, very similar terms for x1 and x2, just different signs. So let's take the Laplace, the inverse Laplace transform in both of these and get our x1 function and our x2 function in terms of t. So when I do this, I have negative, right? That negative is still there. 1 over s squared plus 3. Okay, and if you notice, we're almost to what we would like in terms of a sine or a cosine function, right? Because we have the plus on the bottom, but we don't have s or k on top. So we don't make an s, but we can make a k, right? So s squared plus k squared, so that means that k is root 3. So I'll multiply this top and bottom by root 3 to get it to all be nice. And so then for x1 of t, I have negative 1 over root 3 times sine t root 3, or root 3 t, however you want to write it. Okay. Obviously for x2 of t is going to be very, very similar, but without the negative. Okay, I still have to use the same little multiply by 1 trick here. And so my x2 of t is the same function, but without the negative sign. And there is our system, our solution to our system of equations.